Okay, I'm gonna keep going on with the FP course, Data61 FP course. I'm gonna figure out what we were up to last time. Looks like we got to compose and traversable. Okay. So it looks like we skipped state t, extend, comonad. I think that's fine. I'm gonna actually skip list zipper and go to parser. Let me make sure that we've done all the traversable though. I think we did. No, we didn't. Okay, we got to sequence. We got to sequence in traversable. Okay, cool. So we've got a couple more things to do in traversable. Okay, so the first one we're going to do with traversable. So last time we did our compose. So we wrote down applicative, functor, and we tried to derive monad for compose, but there is no monad for compose. Monads do not compose, but traversables do. Traversables do compose, and so that's the exercise that we're going to work on now, which is write a traversable instance for compose. One thing here I didn't do is use instance signatures, so I'll do that. It's easy. So I'll just put in a hole here. Actually, I need to open tmux. Okay, so we have this. Should look something like that. I'm gonna rename this. So that should compile. Well, it shouldn't compile, but it should. We shouldn't get an error about the type. Yeah, there we go. Okay, so that's fine. So we've got a hole in the right place now. So we have to implement this. Okay. So we've got an F. Whoops, what happened there? Got an F and we've got to compose FGA. Oh, compose isn't. How come the type works, but the data constructor doesn't? No, that's in scope. I didn't get that. Should be able to match on that. Oh, it's not actually exported. Interesting. It's not actually exported. Well, we can't really do much with that, so we'll export it. Okay, now we're getting better. There we go. Okay. So if you remember anything about, hey TS Oding, how's it going? Can you tell me how to pronounce? Is there a particular way you like your username pronounced? I always call you TS Oding, but it doesn't sound right. To Soding. Yeah, so if you remember from last time, the way that to think about traversable is that it's a way of deconstructing a data type and then reconstructing it back up inside of an applicative. So given an applicative, you can deconstruct one data type and reconstruct it back up inside of your applicative data type. So here for compose, we're going to deconstruct the compose and then reconstruct the compose back up inside of our applicative. And what we know about compose is that both of these type constructors themselves are also traversable. So we've kind of got like, we need to deconstruct the compose and then we need to deconstruct each of the F and G inside of the compose. So at the moment we have F of GA. Like a single tss sound, okay. Soding. Soding, something like that. Okay. Right. Okay, yeah, I thought it might have been like a language thing. Yeah, fair enough. Okay, so we got so we got an F of GA. We know that F is traversable. It should say that somewhere. It should say that up here. So maybe it doesn't. No, it should say. It probably did. It should say somewhere that that's a traversable. Well, it is. We know that F is traversable. We know that G is traversable, so we need to do something with this F. Actually, we'll do that. Let's focus on the to-do one there. What should we put into that? If we want to traverse F, what can we traverse it with? Well, pretty much any function. That's not very useful. It's a good way to do this. Well, we know this is going to give us a GA. Oops. So what we have in scope now is a GA. Yes, I saw that. I saw you tweeted out the next Game of Life thing. Yeah, I saw that this morning. I'll have a look. I haven't actually looked at the code yet, but yeah, that's interesting. I'm guessing, did you just use the trace function to do the console output, I guess? Let's have a quick look. Yeah, trace, cool. Oh yeah, trace. Wow, yeah, actually using it as a programming language, that's awesome. So does the module use trace, or does it just the README? Oh cool, it doesn't actually use trace inside of here. Oh, I mean you inherit it, but... That's awesome, yeah, so it's just representing it as lists, I guess. That's awesome, good job. Like Nix is pretty tricky to use as a general purpose programming language, so it's awesome that you did. Yeah, it's really good. Like Nix is pretty much pure except for the trace function. Pretty much everything else about it is pure, so it's really good, and it's lazy as well. So it's like a lot of things that we can express. I don't know, things that we can express more simple and using laziness also works in Nix. It's awesome. The only thing it needs now is types. Just need some types. Okay, so we need to give back an F1, B1. These are, you can see that these are type variables, so we can actually specify what we want to return here. So it's up to us, and that's because we've got like this let. So we're not actually like constraining the return. We can return whatever we want. But we do know what we have in scope, so we've got a GA in scope now. And what do we know about GA? We know that we can traverse, so we're going to traverse again. I'm going to do that. Just because I know, the only thing that we really know about F and the only thing we know about G is that we can traverse them. Yeah, Nix is like a direct implementation on top of language calculus. Yeah, I mean, it's getting that direction, yeah. the scoping rules around, like, you've got this width. You got width, kind of like how JavaScript used to have a width function, or a width statement, I guess. And so that makes some weird things around scoping. There's a couple of problems with Nix, but the good thing about Nix is that it's pure. Really, really good to have a pure description of a build. You don't want to have side effects to determine a build. Okay, so now we've got an A in scope. So we've traversed and we've traversed, and we've got an A in scope now. And what we can do with A is use our function. That's pretty much all we can do. That's the only thing we can do with A really, is use our function, apply our function onto it. So I'm going to do that. Let's put our function in here. And if we look at what X is now, it's a HFGB. And what we have to return is a H compose FGB. So if you look at the FGB there, that is the same as that, it just doesn't have the constructor around it. So if we just did, if we got rid of this, did compose, that's it. And we can also delete this, remove the thing on the left hand side. If it's on the left hand side, you can delete it on the right hand side. And we end up with that. And I think that's a pretty good implementation right there. So composition of traversables is just to traverse them both and then, you know, wrap them back up. So the traverse function itself actually composes. It's pretty good. You could actually write it like I guess it's like this. You could also write it as. Is that right? Yeah. So you can either write it like how I wrote it before, or you can write it like that. I think this is pretty cool. It shows that like if you compose traverse, you actually get a new traverse that works for a bigger data type. So traverse composes. So that is an instance for our compose data type. But there's a couple of different ways of combining type constructors. So we've got compose, which is to have one type constructor around another type constructor. So if you have an F and G, it's F of G of A. But you could also have the product version of that, which is you've got an F of A and a G of A. So it's kind of like a tuple, but over type constructors. So we're going to implement a couple instances for this and show how it works. So I'm gonna use the what's it called again? The instance signatures again. So I'm gonna put in here a whole copy over this. Whoops. Okay, so we have a function, we have our product type, FA and GA. And so we have to give back a product FGB. And we have this in scope. And we know that to make a product, we have to use the product constructor. So we need to give back a F of B and a G of B. And that's what we need to replace these holes with. If we look at what's in scope, we have a G of A, F of A, and a function A to B. And what we also know about F and G is that they're functors as well. So if we have a F of A, what can we do on F? Well, the only thing in functor is fmap, so we could fmap that. And we have this function here. So fmap, F, with this function, would give us back an F of B. Which is exactly what the whole needs. If you look at the whole, we need to give back a F of B. So we can just put that in there. So what is it? F, fmap, fa. And now we don't, now we've got just a B hole. So let's F, GA, there we go. Cool. So that one's pretty straightforward. If you just, to compose, or to make a product of two functors, you just fmap both sides of the functor, that's easy. So this product type also has a traverse instance, a traversable. I'm gonna rename this F1 because it keeps getting confusing when you got F1, and you got a couple of different ones. So Traverse has an F and a product. Okay, so we have to give back a H of product FGB, and what we have is a FA and a GA and this function. So we could run this function. So if we know that F and G are traversable. F and G are traversable, therefore we can run traverse on that. We have this function to traverse with, so that would give us a H of GB and a H of FB. Let's do that. Okay, so now we've got a H of FB and a H of GB. Okay. We need to use those in some way to create a H of product FGB. So if we if you remember what we have, what we know about H is that it's applicative. So we've got these two H things here. We've got these two H type constructors here. What can we do with H? Well, we know that it's applicative. If you remember back to applicative, can't browse it. If we go to applicative, one of the useful functions is this lift2 function that we have, which is a way to combine these two. If you've got a value, if you've got a type constructor with a value inside of it, you can use this lift function to lift a function over those two things, and you get back one thing, which is what we want. We want one H product, and what we have is two H's. So lift2 is a way of taking two things and then combining into one and doing something with these values. So I'm going to use lift2. I'm going to just inline these. Okay, so now what we have to fill in to make this type check is this. F of B, G of B to product FGB. What does this? It's actually the definition of product. If you just substitute the type variable B for A, then you get this. So what we can just do is, instead of using to do, we can product. So remember that Traversable is like deconstructing your data type and then reconstructing it inside of the applicative. That's exactly what we're doing. We're deconstructing the product, which has an FA and a GA, and then reconstructing it, like traversing those, because you have to traverse, like you have to recursively kind of deconstruct the data type. But then we can rebuild it back up in rebuild it back up basically, and we can use lift2 and then our product constructor to rebuild it back up. Okay, so that was product. So product has quite a few instances, but two of them are functor and traversable. And it's just a way of representing two type constructors and a type, and represent that as a value. Yeah, I'm still working on the function programming course. I'm working on Data61 FP course. I am working through this is the Traversable module. So we're working through this one right here, Traversable. Almost finished with this one, and then we're going to move on to, I think, Parser. Next one is going to be Parser, I think. Cool. Okay, so co-product is kind of the is the other. So if product is kind of like tuples. Product is taking two type constructors and then combining them together to make a way of having both those values, having a value for one type constructor and a value for another type constructor. Coproduct is like either. It's like a disjunction type. It's saying that we can have either a value of one type constructor or we've got a value of the other type constructor. So here we usually, this is, I don't know, we usually call this like left, and that one called right. I think this usually stands for inject to the left and inject to the right, but we'll just call left and right. And so this has a functor and traversable instance, just like product does. So let me copy in the typed integers. So what's interesting is that for product, what we do is we just pattern match on the product constructor. But because we actually have two constructors now, we've got left and right. So now we have to do separate patterns like this. So we've got an FA if it's left, or so I'll put that left, and this one will be right. And that'll be right with GA. So now we've got two holes to fill in. So we've got one where we have to return we have to return the same thing in both of them actually. We have to return a coproduct FGB. It just changes what we have in scope. So we've either got an FA in scope or we've got a GA in scope. So fmap. This one's pretty straightforward. If we have GA in scope, if we have FA in scope and we've got this function and we know that F can be mapped, so we can map this to get an FB. This needs to be coproduct FGB, and the two ways we can construct it is either left or right, and the only way that we can do it is left. The only thing we've got is an F. So really all we can do is this. It's pretty straightforward. And then similarly the right one will be the same but on the other side. Pretty straightforward. So let's do the so that was functor. Let's do traversable. Okay, what do we have? Got a hole, put that in, and remember the same thing as what we had before. You've got two different, you've got FA and a GA. So we have to return a H of coproduct FGB now. And we have a FA and A to HB. The only thing that we know about F is that it's traversable, so I'm gonna guess that we're gonna do a traverse. So now we have this H of FB, and we need to return a H of coproduct FGB. So let's map that and see if we can create a coproduct from that, from our HGB. Reload, and yep, that side is done. Just let me okay. And I'm gonna guess that, actually get rid of these parentheses here. Gonna guess that this is the same but on the other side. Cool. That was it. That's Traversable. So we what we just did is we implemented traverse for compose, and that just means that the traverse function actually composes. Traverse function composes. And then we went through and we implemented product, which is a data type that has two type constructors, but it's as values it has both of those type constructors as values. And fmap and traverse we implemented for that. Fmap was just fmapping on both sides of it. Traverse was traversing on both sides, but then reconstructing up the product. And then we had coproduct, which is where we have a type constructor on. We have one value. We either have a value of one type constructor or we have a value of the other type constructor. We've only got one value of a type constructor at a time. And fmap was just if in case it like case match on it. So case if it's left, then you reconstruct up the left, but fmapping over left and right is the opposite. And then traverse is similar. We traverse on the left and then we reconstruct up the reconstruct back up. Pretty straightforward. And that's just to show that traverse is a way of kind of like deconstructing data and then reconstructing it back up. And so there's kind of different types of data. We've got composition of data, or we have product of data. So if you've got data that has like multiple fields inside of it, that can also be traversable. Or if you have something where you've got sums, or if you've got kind of both sides of things, so you've got like multiple options, but they both have both are traversable, then you can traverse back up. So basically it's a way of traversable is a really like general way of deconstructing data and reconstructing it. Which is really useful because you can use it with any applicative. So if you kind of want to deconstruct data and then use state over it, for example. So if you want to deconstruct it, run state over the fields, for example, count how many fields there are or something like that. Traversable is the way to do it. So traversable, you can like kind of like write count, which will like count all the elements inside of something, or you can kind of, I don't know. There's a lot of different like applicatives that you can use. There's an infinite number of applicatives you can use with traversable, and it's just a way of deconstructing data, then using some sort of applicative function inside of each one of those elements inside of the data. Really, really useful thing. So if you've got a general data type, you can deconstruct it and reconstruct it, and do something while you're calculating through that data type. Really, really useful. Okay, so now that we've done traversable, I don't know. I don't think this module sets up the best motivation for it, but it does show you what it is, which is useful. I think we could do better in this. I wrote the traversable module, so that's completely my fault. But I think we can do better with that traversable module. It sets up the sets up what it is, and I think it pretty accurately describes what it is by showing like you can deconstruct data and reconstruct it inside of products, sums, and composition. But it doesn't really set up why you would want to use it. So I think we can do better in that. But anyway, we're gonna move on because I don't have that done. We're gonna move on. We're gonna do Parser. There are other modules that we could move to, but I think a lot of people like Parser. A lot of people at work did the course with the Data61 people recently, and they really like the Parser module. So we're gonna go there. We're gonna skip this. These things are okay, but I don't know. They might be a little bit tedious. I think. We want to do this. We want to do this quickly. So I'm gonna skip that. List zipper is not very interesting to me, so I'm gonna go straight to Parser. I think. Yeah. And then I don't know if I wanna. I don't know. Maybe I'll play around with these. I don't know. We'll see. Okay, so the first thing is we've got an input, which is characters. Remember that characters. I don't know if I've seen it. We've shown it before actually. But characters is just a list of characters. Then we got this parse result of A. So we've got all of these different error cases. If it's unexpected end of file, if it's an end of file, then we actually had input, list of characters remaining. If we hit a character that we didn't expect, that's unexpected character. So we've got all these different errors, and then we've got this result. And this input here is actually the remaining input. So if we're parsing something and we come up with a result, then that's what we fill in. We fill in this result. But then this is the rest of the input that we didn't consume yet. So we've got this show thing, which is just a way to convert into strings. Got a functor for that data type. And we've got this thing, checking whether it's an error. And we've got this thing which runs a function if we did actually get a result. Okay, and now we've got this thing called a parser, and a parser is, well, there's only one constructor P, and a parser is a function from input, which is our list of characters. If we go info, input, it's characters, and characters is a list of characters, so list of characters to a parse result. So we can write a parser that takes, and a parser is just a function. There is this constructor in there, but that constructor is not very interesting. This is the interesting part. It's just a function from list of characters to some sort of result. So this result could be an error. So if we try and parse something and we hit an error, we can return an error, or we can return our actual result constructor as long as we give it the A, and we have to give it the rest of the input that we didn't consume. So we can consume as much of this list as we need to produce an A, and then we return the rest of it when we return a result. Okay. And parse just extracts out our function and lets us access the function. So it just unwraps this P and gives us back a function. Okay, so let's try this. Unexpected character parser. The type of that is a character tool parser, so let's give it B. So let's say, so I think the way this works is that if we say, so you can see it's a parser, but if we run parse on it, remember parse unwraps the parser and gives us back the function. So now we've got this function, input to parse result. So let's give it an input, let's say hello. Unexpected character B. So I think this fails for everything, right? Yeah. So always, yep, so you can see the underscore here, it always gives back an error. It doesn't matter what you give it, it doesn't actually use this input. It doesn't matter what the list is, because we've got this underscore here, we're not actually using it. It doesn't matter what we give it, it's always going to give back this error. And it looks like they've written a generic version of that, which, you know, const is the way of writing this underscore. So it looks like they've written a generic version of that. Just could fail. Okay, so there's a parser for natural numbers, it looks like. Parser that produces 0 or a positive integer. Let's try it. So parse natural. We'll say. Okay, so we need to implement this bind parser thing. Looks like we're going to implement that later on though. Okay, so I think we're going to just go for value parser then. I think that's the first exercise, and we'll eventually hopefully get to the bind parser. Yeah, that's only a little bit down here. Okay, cool. So we'll start off with the value parser. So value parser is something that always succeeds and consumes no input. So we've got this A, and the way to construct a parser is P. So let's fill in this. Now it wants a function because we're using P. P takes a function. So input. We need to give back a parse result, and we got this input. We have an A. Okay, so we want to always return success. If we go back to our data type, success is the result. So we need to return back a result. Okay, and result takes two things. It takes an input and it takes an A. We have an A, so we can put that in. Now we have to give back an input. And we also have an input actually. And that's what we need to put in there. We need to just put in this input. Because up here it says consumes no input. So to consume no input, you just give back what you get in. So we've got this input given to us. We can just return that. There we go. So we've got a value parser. So this parser will just always succeed with whatever. So if I gave it that and I parsed it, there you go. Return a parser that succeeds with the character off the input or fails with the error. Okay, so now we need to construct a parser that returns result returns that. There we go. Give an input, so we have to give it back an input and we have to give back a character. So how are we going to do this? I'm going to pattern match on the input. So what this means is check the input. If it's empty, do something. If it's got an element, do something. So I'm going to call this so if we actually have an element, like if we actually have a character, then we give back what we've consumed. Like this is the rest, right? This is the head and the tail. So the tail is everything but the first character, and C is just the first character. So we can just return the first character and the rest of everything. And for the nil case, what do we need to return? I think there's like an unexpected end of file. I think that's what we want. Unexpected end of file. So we hit the end of the string, and we expected it to not be the end of string. So there we go. That's that one. So that's the character parser. Let's try this one out. Parse character. So there you go. So this one parses just a character. It gives us back the rest. Actually, let's try it out with empty. Give it empty, unexpected end of string. Cool. Okay, so to map a parser, so we have f to map a parser of a. We need to get back a parser actually, so let's do that. Actually, we know that the parser takes the input. It always takes input. Okay, so we need to give back a parse result B. What do we have? We've got a to B, and we have input to parse result A. What can we do on parse result? Okay, so there is a functor for parse result. There you go. So there's a functor for parse result. We could use that. So what we can see is that if we did this, so let x equals we've got the input, so we can actually run this. So remember that A here is actually a function input to parse result A. We've got our input, so we can actually supply this input to the here, and then we get back a parse result of A. So let's relate this. We should have access to a parse result of A now, and we can fmap that. Parse result has a functor instance. If we look at info parse result, actually this probably won't. Let me just make this compile. And then we can, info parse result, and you can see here functor. There is a functor for parse result, so we can actually use fmap on our parse result. So we can actually fmap this part with our f. And there we go. And we can refactor this slightly. We can actually do that. I'm gonna call that one G. There we go. Cool. So we can map a parser, and the next one is going to be bind a parser. So this is like the monadic bind that we've seen before in monad. So this is like bind A to FB, FA, FB. The F has become parser. So A to parser B, parser A, parser B. So F. And we'll call this one parser G. We need to get back a parser. Actually, we might be able to use this function actually, so let's have a look at that. Whoops, let's call P. Okay, so we have input to parse result A. We need to get back a parser B. Okay, so we don't have an input, so I think we are going to have to use this P to get an input. Go with that. Okay, so now we've got an input. Let's parse it into this. Let's put it into this G thing. So G. that. Now what do we have? We've got a parse result A. What can we do with that to implement that? Well, to use for that function. I think if we look up above, there was a function that we saw. There was this onResult thing. That looks useful. OnResult looks useful. We've got a parse result A, input a parse result B. Give back a parse result B. That seems close. Let's see if we can use that. So what do we need to do? OnResult. We might actually be able to do OnResult. Got this in here. So let's go OnResult G. Then these are functions. Let's talk about that. Nope, that wasn't right. Oh, onResult is for parse results, is it? Yeah, it's not for parse results. We do actually still need to construct this. Okay. We might need to do this though. OnResult. There we go. Now we're going in the right direction, I think. There we go. So now the hole we have to fill in is input a function that takes an input and an A and a parse result B. So input prime. So now we've got two inputs. Input prime A to something. Okay, so we've got an A, we've got input prime, we've got input. Now we need this thing. So we have an A actually, so we could actually give back a parser B. So let's do that. Because we've got the A and we've got our F, so we can go FA. Let's go with that. Whoa, what's happening? Okay, so in order to give back a parse result B, what do we have? We've got a parser B. And if we run that parser, we have to give it input prime, I think. So let's try that. I'm gonna inline this. Let's go that. There we go. That I just followed the types there. I've never implemented this function before, so I'll just follow the types there. I'm gonna lay this out very slightly differently. Something like that. Okay. So we get our input, use this onResult thing. So we run the thing, and then we have to run it a second time. Hey, Interpsy. I have been posting this to YouTube. If you go to my YouTube, I don't know where it is. Hey, Silent Planet. I'm not probably able to help with C++ stuff. I am not good at C++ at all. Wonder if there's a. Nope. Videos of me, but none of my channel's not coming up. There we go. Here I am. So I have been uploading these to YouTube. If you look at some of the recent ones, there we go. Here's one of them. So I've done number 1, number 2, number 3. So this will be number 4. I will upload this one up to YouTube afterwards. You can check them all out on there. I've got the whole series up on there. Sorry, Silent. I pretty much do mostly functional programming. I'm okay at some C, but I'm not very good at C++ at all. Return a parser that puts its input into the given parser, and if that parser succeeds with a value, ignore that value, but put the remaining input into the second one. Okay, so this one just consumes with and ignores the value that we get back. If it fails, return the error. Okay. So we've got two things. We've got a parser of A and a parser of B. And we need to give back a parser of B actually. So what can we do on this? Parser of A, parser of B. We need to do something if this one succeeds. So if this one succeeds, so if you think about bind parser, we've got a parser of A, and then we're like, if we get an A, then here's a parser of B. So this is so it looks like bind is most of that. So if we go bind parser FA, actually I need to flip that, don't we? Whoops, not FA, PA. Okay, so now we need to give it an A to parser B, but we said that we don't care about the A. So we could do that. That type checks, because you don't care about that. And remember, this is the same as saying const. So that type checks and says that if PA succeeds, then ignore the A, give back PB. But if PA fails, then we'll give back the failure. So that satisfies the spec up here. The spec was if it succeeds, ignore the value, give back to B. If it fails with an error, give back that error. Oh, here we go. It even says here, use bind parser. So there we go. Use bind parser. Straightforward. Join a parser that tries the first parser for a successful value. If the first parser succeeds, then use this parser. If the first parser fails, try the second one. Okay. So this is try this one. If it succeeds, then use it. If this one, but if it fails, then use this one. So it kind of falls back to this one. Okay, so this one's a tricky one. PA and PB. Are there any hints on this one, like the last one? No, there's no hints. Okay, so we'll just implement this one then. So we need to give back a parser. So this one's got input. And so it doesn't say anything about consuming input, but I'm guessing that if we want to try it with the same input, because if the first one succeeds, if the first one fails, try the second one. We don't want to try the second one with the rest of the data. We want to try it with with all of the data. So here we go. Yeah, this is there a good example here? Value parser B. No. Yeah, there's no good example there. Actually, there is here, because we return here. We actually have the whole input here. Okay, cool. So we have to make sure not to consume the input when you're on the second one. Okay. So let's run the first one. So this one's a go with that. So now we've got this parse result. So we need to check if this one's an error. If it's an error, then we go to this one. We go to the second one. And there is, I think I saw something up here which is like is error result. We can use that. Let's go with that. So let's say if this is an error, okay, so we have to get back a parse result. Or a parse result. Okay. So if it's an error, then we have to go to the second one. So then I'm going to extract this one, PB. So we'll run the second one on the input. Otherwise, we'll go back to the first one. There we go. Cool, so that type check. So I'm going to add one little thing, which is I only want to run this function once. I don't want to Don't want to run it twice. It won't really make a difference because it's just a parser. It won't really make a difference, but we'll do that. So, way to read this is just, we run it, check if it's an error. If it's an error, go to the second one. Otherwise, otherwise we use the result. So if it was a success, just use the result. Cool. So hopefully this one, let's try this one. Cool, so that is the same. So, first one failed, so we just moved on to the second one. Let's try it the other way around, let's try if the first one succeeds. Yep. That's the right result as well. Cool. Okay. Use list one value parser and this or. I'll pronounce this alternative because that's actually what it is. It's meant to be the alternative function. So return a parser that continues producing a list of values from the given parser. Okay, so we'll just keep retrying the parser. Just keeps retrying it. Okay, so use the or. Okay, that makes sense because we're going to keep just retrying it. Value parser. Okay, so I guess that's to handle the empty case maybe. And list one. Where's list one? Oh, we haven't done list one yet. We haven't done list one, so I think maybe we should do list one. Oh, but list one is implemented using list. Hang on. So we have to use. So to implement list, we have to use list one, and to implement list one, we have to use list. That doesn't sound right. I'm not sure about that. Maybe it'll work out if we did that, but I'm not sure. I'm actually gonna go to the repo and just make sure that that wasn't something that's been changed. So list one says, okay, looks like they've renamed bind, but that's okay. Okay, it does say that. Instead of pure, it says, okay, instead of value parser, it's got pure. Okay, so it's made it more, it's changed a couple of the identifiers, but nothing serious. Okay, so it does say use, in list one use, in list use list one, and in list one use list. So it does say that, so I'm gonna trust it for now. Well, let's just assume that list one is implemented then. So list one will return a parser that produces at least one value. So it looks like list one is like list. So list always returns the result. You can see here it always returns result. It doesn't matter what you give it as an input. It looks like it always returns result, and just the result might be empty. That's all. So it looks like if we implemented this, list one, let's get this, so list one of parser, so that would type check, but list one fails when it can't create a, see here, it fails. It fails when there's not at least one character. So what we could do is say, try list one, or nil. So if list one fails, then give back the empty list. So this will handle the case where list one doesn't, like list one is given an empty string. So if you see here, if you give it an empty string, or if it doesn't parse, if it doesn't parse, then it'll be an error. So I think that's an implementation for that. I'm not confident in it. I'll test it out later after I implement list one down here. So this one produces at least one value from the parser, continues producing a list of values up until they produce a non-empty list. Okay. So this one says to use list. So this one will just be list. So that, I'm just using that to type check. But what do we want to do? We want to continues producing a list of values from the given parser. This one's tricky. Use bind parser and value parser. Let me think about this one. I think that's right. That looks right to me. List one. Yeah, I think that's right. I think I might have to come back to this one. This one's interesting. Use bind parser. Use bind parser. I don't know how we can use bind parser. That seems... I'm gonna come back to this one actually, because that one's... I don't think we can do this one with just bind parser. Bind parser list and value parser. Maybe we can. What else we got? I feel like there's another function that we're missing here. Yeah, it just says use bind parser. Okay, maybe we can. Maybe we can. We'll give it a go, I guess. Yes, maybe we can, yeah, actually. I'm gonna try it. Okay, let's just try it. So let's, what can we do? We've got this PA, let's bind on this one. We'll try this one out. Try running the first one. Whoops, where am I? There we go. Try running this one. Okay, so we've got an A now. So we'll try, I think this is the trick. We try running the first one, then what we should do is try and get a list of them. Yeah, that makes sense. So try the first one, then try and get a list of them. Whoops. And then what do we do with that? If that succeeds, then just cons them together, I think. Yeah. Actually, that looks like... Doesn't that look like lift 2? Try the first one. Try the list of them. Yeah, I think that looks like lift 2. I'm gonna try this. Try the first one, then try a list of them, and try and cons them together. Is that right? That type checks. Let me try this. Oh, we haven't got an applicative for it yet. What can we do? Let's go through the instances because I'm going to use them. I want to use them. I guess what you're meant to do, because this is use bind parser, so you're not meant to use lift 2 yet. I guess. Let's do that then. Let's go with what it says. Sorry, I haven't done these ones before, so this is all new to me. So I'm just going to translate it in my head to like what the applicative syntax means. List of PA. So this is all equivalent. You can do this once you get okay with this syntax, with knowing what applicative does. This will make sense. I think that you can ignore that. But, whoops. Just know that this is the same. It's just, we bind the first one, like, bind the parser, try it out. Try out getting a list of them then, and then we cons them together. So get out, try a head, try the tail, and construct a cons out of it. Okay, so that makes sense after I realized bind. Oh, come on, I reloaded, didn't I? I'm not using applicative, am I? What have I done there? I didn't use the applicative anywhere else, did I? No, I'm not using it. Interesting, I don't know why. I don't know why there's an error there. Oh, because there's applicative right here in the actual example. So we do have to implement applicative for the example to even run. That's annoying. Okay. I think I will. Hang on, that's not the right answer, is it? Oh no, it is. Oh yeah, because it's Parser list of it. Okay, cool. I'm gonna implement these. I'm gonna implement these because it's annoying me that we don't have access to these. Okay, use bind parser and value parser. So we've got a F. We've got a PA here, so this gives us an A. Then we do value parser F of A. Pure is value parser, that one's easy. And there's just the types line up there. This is PA, PB. Oh, actually, we gotta. Let's get out the function. So this is our A to B function. Well, whoops, we don't have actually have that. There we go. So that's our A to B. Then we have a parser of A. And then we get back a value parser of AB A. Let's call this one F actually. I mean, actually, there's actually something here. If you notice, it's the same thing as what we just wrote up here. So we can actually change this to fmap. We can actually drop that as well. So that should compile, cool. And that is exactly the same as blind parser. Same thing. Okay, so now we can run our examples. We can actually do lift 2. We can do that. Whoops. Cool. Okay. So if we say, is this an error? True. Okay, good. So that's an error. That should parse the same thing. Yes. Cool. So we did that one right. Okay. So lift 2 works. Sorry, list 1 works, and also list I think works. Let's try this as well. Come on. There we go. That's correct. Yeah, that's all working. And we'll try this one, last one. Oh, we don't have digit. Okay, so we need to implement digit as well to test that one out. But we'll just keep going in the list. We'll just keep going down. Okay, return a parser that produces a character but fails if the input is empty or the character does not satisfy the given predicate. Bind parser, unexpected character, and character parser functions will be helpful. Okay. Parse satisfy is upper. Okay. So let's take our function. We need to construct a parser. Input. Actually, we already have this character parser, don't we? Let's use that. We already have that. So that'll give us the character. Then it says use bind parser. So let's use that. Cool. Okay, so this one takes a character, and that's when we can. What we have in scope is character, and we also have a function character to boolean, so let's use that character. So the x will be a boolean, so now what we can do on that, deconstruct it using if. So what do we do in the successful case? If it parses, then we return it. Now if it succeeds the predicate, then we use it. Otherwise, I said use the unexpected character. Yeah, unexpected character parser. Is that what we do? Unexpected character? Yeah, there we go. So we just use if it fails the predicate, then we return unexpected character. Cool. So let's try this. If it satisfies is upper, give it back. If it doesn't satisfy that, it's an error. Cool, so that's it as well. Return a parser that produces a given character but fails if the input is empty or the produced character is not equal to the given character. Input is empty or the produced character is not equal to the given character. Okay, so use the satisfy function to implement this. Okay, so if it is this one's easy as, is it equal to the character? Is C equal to the thing? So there you go. That's really simple. I think that can even be written like this, can it? There we go. Same thing. Yep. Pretty straightforward. If it's equal to the character, that's it. So digit. Okay, so we've got this character is digit function, and we've got satisfy. Okay, well that one, what is it? Satisfy is digit should be it then. I'm guessing, I don't know what the type of is digit is. Is digit, character to bool, and that's the same type, so digit. Let's try this one out. Yep, that one's real straightforward. And then we can also take a list of digits. Or list one of digits. Cool. So we've written a parser for digits. Return a parser that produces a space character but fails if the input is empty. Satisfy and is space. So satisfy is space. I mean, they're giving us the answer by the tips here. Satisfy, use satisfy and is space. How do you use those two together? Well, is space is character to boolean. Satisfy is character to bool. Takes a character to bool and gives it a parser. So really straightforward. Space is one. Use list one and space functions. Is this just list one space? It probably is. Return a parser that produces one or more characters. Yeah, that's it. That's it. List one. Use list one in space. Okay, thanks for the implementation. Use satisfying is lower. Okay, thanks for the implementation again. Satisfy is upper. Okay, now it looks a little bit. Sequence parser. Oh, okay, so a list of parsers to a parser of a list. Trying to parser that sequences the list of parsers by producing all of their results, but fails on the first failing parser of the list. Use blind parser, value parser. Optionally use fold right, if not an explicit recursive call. Well, we'll go for fold right. We've had enough practice with fold right in the in the first in the part 1 that I did. Part 1 we did a lot of practice on fold right. And remember, fold right is constructor replacement on list. Well, fold right is constructor replacement. Fold right on list is, replacing the constructors in list. So fold right takes two functions, takes the replacement for cons, takes the replacement for nil. and then it takes the list and it replaces all of the occurrences of cons and all the occurrences of nil. There'll only ever be one occurrence of nil, or at most one occurrences of nil in a list, and we'll replace that. So use fold right, we had a lot of practice with that, so we'll do that. So sequence parser. Sequence parser, remember, also looks like what we were just practicing, which is traverse, or traversable. If you look at this, whereas sequence A we had. So look at that, TFA, FTA. So notice that this lines up right. So we've got an applicative F and traversable T. So if we go info on applicative, it'll show us everything that is implicative. And I think in here you'll see parser. Yeah, there you go, parser. And if you come in here and you look at traversable, you'll see list. List is traversable. And so these types actually line up, sequence A. So we could actually just do sequence parser is sequence A. I think that should work. Is that not right? Oh, it's not imported. Let's say if we had this imported. So that actually compiles. Let's try it out. That is the right result. And here, let's hope this is the right result. True. Yeah. So that is actually a valid implementation. So we could actually just get it for free. Get this function for free if we just recognize, like, just by writing the applicative for parser. We've already got the traversable for list, and we've written the applicative for parser, so we could just get this function for free. But we won't do that. We'll actually implement it because that's an exercise. We'll implement it. I think when I go to commit it, though, I'll actually use sequence A. Use bind parser and value parser. Optionally use fold right. Okay. So let's use fold. We've got this list. We've got X's, so let's use fold right. Actually, anything we need to do. X's there, we can drop that. That's easy to see. We can drop that. So now we have parser A, parser list of A to parser list of A. So this is replacing the replacing cons, and this is replacing nil. If you remember what I was saying about how traversable works, and if you recognize that this is traversable because we've already seen it, really what you do is you deconstruct the list and you reconstruct it inside of an applicative. Here we know that parser is the applicative, so what we could do is reconstruct cons, but inside of our applicative. Reconstruct. So this is, remember, fold right takes cons and it takes nil. What we're going to replace cons with, and we're going to replace nil with. Replace cons with cons, but that works in parser. So replace cons, but with replace cons with a function that makes cons work with the inside of parsers. And nil is the same. So replace nil with a parser of nil. So here we can say value parser nil. So if you remember what I was saying about how traversable works and how fold right works, you'll be able to figure this out. This is exactly the implementation of traversable for list. So we've already done this. We already know this. We know it's sequence A. It's a good exercise, but only if you don't know much about traversable. We know we just went through traversable a lot, so we know all about this. We know it's just sequence A. Okay. Return a parser that produces a given number of values of the given parser if the parser fails. Well, this parser fails if the given number fails in the attempt to produce the given number of values. Okay. Use sequence parser and list replicate. Okay, so let's use, we got n, and we got our parser, and what do we have? We're gonna use sequence parser, so we've got sequence parser. So it says use sequence parser. I know that our list replicate returns a list, and sequence parser returns a parser, so that's why I'm going to put sequence parser here, because I need to return a parser. So let me reload over here, and it says I need to give it a list of parsers. A list of parsers. And I know that actually list replicate does that, so I'm going to put list replicate in there. Replicate. could look at the type, but probably can't look at the type. Well, there's an error in here. Actually, there's one way that we can set F defer type errors, I think. I don't know. Let's try that. Okay, so it still loads even though we've got errors in there. I think that's useful. So now I can actually ask for what the type of replicate is. Type of replicate, n element, and list of A. We need to give it back a list of parsers, so this A needs to be a parser of A. So we'll give it this the n, we know that. So we need to give it back up. Now we need to fill in the whole as a parser of A. Okay, so we've got a parser of A here. Okay, so that's it. I'm going to drop that. We'll be done. So this many, so we could say this many 4 uppers. And that fails. We could say 4 uppers here. And we get back 4 uppers. Cool. And what happens if we say this many 5 fails, if we say this many 3 succeeds? Cool. Okay, so age parser. Write a parser for person.age equivalent to natural. Equivalent to natural. It's not equivalent to natural. Oh, it is natural. I thought natural gave back a character. It doesn't. Okay. So age parser is equivalent to natural. Okay. All right, because we're actually writing a parser for this thing. I think if you look at the README, it says see also course.person for the parsing rules. Okay, so I think we're building up to this. Right. So we've got an age. So this is what we're doing now. I think in our parser.hs, we're actually writing a parser for this person. So we're taking yeah, we're gonna write a parser for this. Positive integer. Here's all the rules, so we need to implement all this. Non-empty string that starts with a capital letter and is followed by 0 more lowercase letters. Okay. So we need to use bind parser. So it needs to start with, what was it? It said starts with a capital letter. So was it upper? I think that was. So this is the first. This is our capital. And then we need to use lower. So I need a list of lowers. And actually, what we can do is we know lift 2. If we reload that, what we're saying is get a upper, get a list of lowers, and combine them together. So hopefully if we, there we go. Okay, so it says use all this bind parser, value parser, but what we're really implementing is applicative. I think we're used to applicative enough to be able to see that we just want to take the upper, get a list of lowers, and combine them together using that. I think using bind parser, value parser, and that's gonna confuse us more than help us. I guess the idea is that we haven't written the instances yet, but we cheated and we wrote the instances to make this easy. Write a parser for surname. What's the rules? String that starts with a capital letter and is followed by 5 or more lowercase letters. Okay, 5 or more. Interesting. Okay, so use this many lower list. Okay, we can do that. So what we're gonna have upper. We're gonna combine that with our this many, is it? This many 5 lower. And then we're gonna have like any list of lower. So I'm gonna use list 3 this time because we're combining like 3 different sources of our parser. Hopefully that makes some sense. We got, before we had lift 2 because we were combining upper with our lower. We're gonna have lift 3 here because we're gonna combine the upper with the lower and with our other lower. So we're gonna have like 3 sources of values. So we're going A, B, C in here, and then we're gonna have to combine them in some way. I'll show you what those types of A, B, and C are. So we need to give back characters. We have a character which is our uppercase. So that's A. We're going to cons that on with, well, we have a B and a C. So B is our list of our 5 lowers. And I'm going to concatenate that with the rest. So hopefully that makes some sense. We're gonna get the uppercase, cons that on to the lower, and then concatenate that with the rest of the lower. Okay, so let's try that. What's it saying there? Oh, I haven't reloaded yet. There we go. Cool. I mean, these tests aren't very exhaustive, but they'll do for now. Let's see if they. I think that's roughly right. Write a parser for person.smoker must be Y or N. Use is and or. Okay, so we can say is Y or is N. Hopefully that makes some sense. I think that's pretty straightforward. Is Y or is N. Write a part of a parser. Actually, I think there's another way we could. No, that's probably good enough. Write a part of a parser for person phone body. It's possible. Okay, so phone body is in here. Phone. String of digits, dots or hyphens. I must start with a digit and end with a hash. Ignore the overall requirement of a phone number to start with a digit and to end with a hash. Oh, okay, just string of digits, dots, or hyphens. Okay, so we'll ignore the hash and we'll ignore the... Start with a digit, end with a hash. I guess we're ignoring... Yeah, we're just string of digits, dots, or hyphens. Okay. Wonder why we're ignoring the start. So it's a list of digit or it is hyphen. Do you say anything about the hash? List string of digits, dots or hyphens. Okay. Or it's a dot. But here, this thing is not going to... Oh, whoops, I need to reload. Yeah, that's... Oh no, that's right. Okay, cool. And that's right as well. Okay, I got confused there about the requirement for a minute. Okay, cool, so I think we got that. So it's just a list of digits or dots or hyphens. I think that makes sense there. I think you can read that. Okay, so now write a parser for phone. Okay, now this one we're saying must start with a digit and end with a hash. Okay, cool. So this one's putting the more restrictions on it. Okay, so it must start with a digit and end with a hash. So it must start with a digit. Okay, so so it needs to be a digit. So it needs to be a digit, then we're going to use our phone, what was it called? Phone number parser, phone body parser. Phone body parser, let's say lift 2, and we're just going to put these together for now, then we'll have to think about the hash. Okay, so this will... So now it has to start with a digit. It can't be anything else. It can't be a dot, for example. So let's try it with... So before this one would work, if we did phone body parser, this should work, I think. Yeah, so that parses as a phone body, but that doesn't parse as a phone right now. Okay, so that's good. So now we just have to ensure that the last character, like the next one after that, is... is a hash. So let's actually just do that, is hash. What we can do is say A, B. We're going to actually ignore the hash, I think. Yeah, we're going to ignore the hash. So A, B. And that's going to be lift 3. Cool, yeah, unexpected in our stream, so it does need the hash there. Unexpected character, A, and it needs to be the hash. Cool. So we got that. And you can see here that we're actually just ignoring the hash. We don't actually need the hash. We don't actually care about it. Cool. So now we've got we've got all the parsers for a person. We've got age, first name, surname, smoker, phone. Now we just need to combine them in some way. Cool. What are we gonna do? What are we gonna do? Make sure all the tests pass. Okay. Yeah, they do have a lot of tests for this one. That's good. Okay, so use blind parser, value parser, this thing, spaces, 1, age parser, first name parser, surname parser, smoker parser, and phone parser. Okay, so this is going to be a big function. Okay. Okay, spaces 1. Okay, cool. Okay, I get that. Okay. Actually, that's what we could have done up here, I think. Now that I'm thinking about it, we see this, the function that we wrote, which is this. Hang on, where is it? It actually ignores that one. Okay. Yeah. Okay, we can't use that one for the hash. That's fine. We'll use it down here. Okay, so we need to parse. So the way it looks like is something like this. It uses the age. So it's going to go age first. And then, actually, no, that's not what we want. So we're going to use the age. And then we've got spaces 1. But we're going to ignore the spaces. And then we're going to have, what's that? That's first name, right? First name. Oh, thank you for the follow. It's got age, first name. I'm going to lift something. I don't know how many. We're going to lift something. First name, then we've got many spaces again. Surname parser. What's this? Smoker, is it? So, spaces and then smoker parser. And then last one should hopefully be spaces and then phone parser. And how many is that? We need like a lift. 1, 2, 3, 4, 5. We need like a lift 5. We don't have a lift 5 yet. Oh, that's annoying. We got lift 4. But we don't have lift 5. Annoying. What can we do? I'm gonna write lift 5. I'm gonna cheat. I'm gonna write lift 5. It seems like they want us to bind. I'm not gonna do it. I'm gonna write lift 5. And if you remember anything about lift, there was a very regular pattern to it. It's just like this. Whoops, done that 5. Very regular. You just added on another argument. So we've got lift 5 now. It is in scope. Lift 5's there. There we go. So that actually compiles as well. So we just did age parser. And remember that this operator just means like skip, like ignore spaces. Make sure it's there, but ignore it. So ignore the result of it. So we don't actually care about how many spaces there were or what the spaces look like. We only care that there were spaces. So parse the age, find some spaces, first name, spaces, surname, spaces. And then we're just saying lift 5, so combine all of those into a person. So it just passes all of these as arguments to person. Okay, so let's make sure all of these tests pass. I'll just copy and paste them over. True. 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 I think we're doing pretty good. I think we might have it. And this one. So that's all the errors, and this one, yay, we actually got a person back. The person was 123, their first name was Fred, their last name was Clarkson, they were a smoker, and that's their phone number. That's awesome. We did it. I mean, the thing is, like, we can go through and we could implement everything using bind parser and value parser and then do it, but it just gets super nested. And we don't actually need the power of bind, so I think it's better to use lift 5 here. Okay, so I'm happy with that. Okay, looks like there's more parser. How big is this one? Okay, there's quite a bit in this. We can keep going with the parser stuff, but I don't know, I think we kind of got the point there with parser. How we just wrote up some combinators, we just used some functions. Well, a parser is a function. And we can build them all up just by using the combinators that we write based on those. JSON parser, that's an interesting one, so JSON parser. Yeah, that one looks like an okay one. Does this one use, does this one build up on more parser? It does. It's annoying. If it didn't, we could go straight to JSON parser, that'd be cool. I don't know, just doing more parser just seems a bit, I don't know, a bit excessive. It doesn't. You know, there's some good stuff in there, but I think we kind of get the point, that's all. If we had a lot of time, like if I wanted to spend a huge amount of time on this, we could keep going through with more parser, but I don't really want to spend a huge amount of time on it. What's interactive? Let's see if we can go here. Okay, eliminates any value. Okay, yeah. I think that one actually already exists, doesn't it? Functor. Yeah. What's the difference there? Yeah, that already exists. We've already written that one. I don't know why that one. Version of bind that ignores the result of the effect. Yeah, that one probably doesn't exist. Okay, so we can keep going with this. Example program which uses I/O to echo back characters that are entered by the user. Okay, so it's running. So what's the exercise in this? Ask the user to enter a string and convert it to uppercase, convert the string to uppercase, print the uppercase string. Okay, so this is like... Okay. So this is just showing some simple I/O programs from what I can tell. Yeah, I think we'll skip that one. That's not very... We've already gone through like the file I/O. Anagrams, fast anagrams. So this will actually do some I/O as well. Turn anagrams of the given string that appear in a given dictionary file. Compare two strings for equality, ignoring case. Okay. That one's straightforward as well. And then there's fast anagrams. I'm not sure what the difference is here. I haven't done this one, so I'm not sure what the difference is there. Do they have? Yeah, I'm not even gonna do that one. That one's boring to me as well. A lot of these are not very interesting. Let's go check. Let's look at the last one. Write a function that accepts a string and returns a string, or will accept a numeric value as input representing the amount of money and convert it to its described English. For example, if you input 1.11, will result in a return value of $1.11. So I'm guessing that's That's pretty good. That's pretty good. That's pretty good right there. There you go. 456 vigintillion, 789 novemdecillion, 123 octodecillion, decillion, 456 septectillion, 789 sextectillion. Interesting. That's a lot of money. That would be fun, I guess. It's pretty straightforward from what I can tell, is it? Maybe not. I guess maybe not actually, yeah. That one could be interesting. But one thing I wanted to kind of go towards, there's actually some extra ones in here as well. Usually it's in here somewhere. I think I've seen projects. Yeah, here we go. So there's a tic-tac-toe. So that's a good one. And then there's also a network server. Tic-tac-toe is a really good one. It's about like API design. So the goal is to write an API for tic-tac-toe, noughts and crosses, and you have to make it type safe. That's the idea. You have to make it type safe. So it's impossible for the user to break the rules of the game. So if you try and break a rule, it'll say nah, you can't move because you know someone's already won. You can't move. You can't make a move. So that's a good exercise. I like that. Also, they have been working on the Queensland Functional Programming Lab have also been working on a applied FP course. So I'm not sure where to go. I can either go a lot of the exercise in. I think we've done like all the interesting things inside of. Well, we've done the majority of interesting things inside of that sort of FP course. So I'm thinking maybe either I'll go to we'll either work on tic-tac-toe next time. I think that could be fun. Maybe we'll go to tic-tac-toe and we'll try and do a type safe tic-tac-toe. And you don't even have to go like overboard with all like dependent types and that. I mean, you can go that way. You can go like kind of, you can kind of enable all these features in Haskell, but you don't even have to do that. You can just use data types to represent it. Yeah, let's go tic-tac-toe next time. And then maybe I'll check out. I haven't really looked at the applied FP course before, so we'll do. What I'm going to do is, I think I've been going for almost 2 hours, so I'll finish about here. But I think next time I'll work on tic-tac-toe. We'll try and make a type-safe tic-tac-toe game. Hopefully we can do that in a couple hours. Next, actually, yeah, we'll talk about that in a minute. Next time we'll try and do a type-safe tic-tac-toe. And I'll look at the applied FP course. Maybe that's where we go next time. I haven't actually looked at any of these programs. I haven't actually had to go at it. But it looks like we have to make a web server or something. Yeah, we have to write like a web. We have to use web stuff. That's the applied FP doing web things. Yeah, cool. Okay, so it's just returning responses. Okay, cool. Okay, so that's what we'll do next time. We'll go through. If you're interested in the tic-tac-toe thing, have a look at the FP course. Look under projects, and there's tic-tac-toe. Have a look at this and read through this. There's a lot of like there's rules on this. So you basically have to implement all this. This is the API you have to implement. Okay, and it also says write automate test for API. Okay, so we can do that as well. We'll do a good job at this. We'll spend a while on this. Is it 2-player or computer? So I think for the first one it is 2-player. And then I think extracurricular down here, it says write an opponent that never loses. So I think the opponent eventually becomes, yeah, write an opponent with easy, medium, hard difficulty levels. Yeah. So I don't know. I guess we could either write an opponent that's just random, or we could write, we'll just make a 2-player. I think 2-player to begin with is good enough. Cool. So next time we'll do that, and I'll have a look at the applied FP clause and see what we can get out of that next time. Cool. So next time, I'm actually traveling to San Francisco next week for work, so I'm not going to be available that week or the week after, actually. I'm not going to be streaming for probably about 2 weeks. I might try and maybe do it this weekend, actually, if I can get some time this weekend. I don't know if I'll have enough time this weekend. I'll try. I wonder when I can do tic-tac-toe. I want to do it soon, but I'm not sure when I'll be able to stream next. I'll have a think about it. I'll try and put up a schedule on my Twitch page. I'll try and put up a schedule. See if I can think of a time that I can do, that I can at least start on tic-tac-toe. Probably, I think I could do it in probably a couple of hours. Do an okay job at it, but I want to do a good job at it. So we'll write some tests for it and that. And we'll make it pretty good. So we'll spend a little bit more than a couple of hours on it. I'll have to think about when is a good time for me to do that though. So we might start it maybe. We'll try and start it soon, and then we might have to delay it for a little while. Well, that's okay.